Hello? Alright, nice. Let me make sure that this sounds clear enough. Hello, hello, hello. Test. Let's test. Alright. What was that thing I did the other stream where I got rid of the audio? Advanced audio properties. No, it's not that. What the hell was it? Nope. Oh, it was probably filters. Okay, remove. -15. Oh wait, that would increase it. -40. Hello. Okay. About -60. That sounds good, right? I just hate how it does. How I need I don't understand why this mic picks it up so hard. Bro, stop. Need some suppression somehow. This isn't really noise canceling my thing. Is it this? Oh, no, no, no. No, not that. Not that. How can I... Let's use a pair of pants. Oh, wait. I'm a genius. Just put it right here. There you go. That sounds terrible. Alright. Why is this mic so damn sensitive? Let's put it there. Alright, let's just switch it back. I don't care. There you go. Okay, what I was trying to do was I was trying to make it so the keyboard will also kind of peek through. But it's too much of a fucking hassle to get that working. So I don't care. Because I don't like how, like, if I don't talk for a while, it's just like code moving on the screen. I like hearing, like, typing. But I mean, I'll figure out it later. Alright, well, everything's good. So we can get into the stream. 8 minutes only of taking a bit. This time I'm not going to forget to turn on the work timer. There you go. Boom. Already turned off. So that's good. We got that working. Those, everything's working. Music's in. And we're good. Good to go. So, for those who tuned in for the last stream, and then I'll just say start 8 at like 9 minutes. Okay, so start at 9:00. So, for those who tuned into the last stream, we spent 4 hours. I already explained what it was. We took 4 hours and we didn't get it working, but we got very close. So I had to kind of like tap out and call help from a friend. And it's my friend on the competitive programming team. And he's really good with his data structures and algorithms. And he came in clutch. So we were able to talk together and figure it out. And here's the solution. Again, we kind of went through most of the edge cases, I think. I think we found most of them. So it'll be just pure implementation this stream. And I also to clear up how the simulation is going to work, I'm modeling this off a submarine game that I play a lot. And basically what's going to happen is you have a breach inside your submarine. Obviously water needs to pump into the system. So basically what you can think about this as is different rooms, and there's like a leak that's happening and water's flowing in to the system. And yeah, so there shouldn't be any air pockets and shit like that shouldn't happen. But let me draw this out. And I also like the way that we decided to draw that when we were working on this together, because the connection lines were a lot more clear. Put this up here, this right here, this right here, put this right here. Okay, so this is what your map would look like. For an example, you can make something like this. We'll label these. This is cell 1, this is cell 2, this is cell 3, this is cell 4, and this is cell 5. Alright? And basically what will happen is is if we mark this as the source node, water would begin to pump into this cell. Now the water would then traverse over to here, because this is at the lowest level, then this would traverse into here, and then it would begin filling this up, and it would fill up, and it would fill up. Nothing else would be filling up. And then this would fill up to this level. Once they match right here, they would be good. They would both begin filling up. They would fill up some more until they reach like this level. And then both of these would start filling up at the same time. So now you'd have something like this, where these all fill up at the same level until you hit this, and then this level will start filling up because they all connect. And then they would all fill up, and then let's say we get up to here, roughly here, so this would be filled up, this would be filled up, this would be completely filled up, and then this would be filled up to like this. And you have this level, but then once it matches right here, what's going to happen is this water is going to go into here. And now what's going to happen is no water is going to go anywhere, because it has to fill up this, so then the water level would kind of stay, at least I'm pretty sure. It would stay like this. Water would start falling into here, and it would go up, it would go up, it would go up, and then they would match, and then once they match, all of these different levels would fill up at the same rate. So, and then obviously it would finish the simulation, they would all be filled. Okay, so that's the idea for the simulation, basically. And we discussed how in this simulation everything was like a map. So you'd have nodes, you had 1, you would have 2, you would have 3, you would have 4, and you would have 5. And for our case, this is literally just directed like this. It's very simple. Where 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 5. And these are bidirectional, so they can go both ways, because 1 can connect to 2, and then 2 can connect to 1. So, bidirectional. And we had the idea where, okay, well, we have these match levels, which is basically what water level does it need to be at for this level to start filling at, which for this case might be 0.4, or like 0.3. This could fill up at 0. This fills up at 0. And then like this would fill up at 0.5, right? So these connections basically have a they have levels their water has to reach to in order to actually go in and fill those squares. So that's kind of like the cost it would be to fill up these squares. And what I'll do to make this actually really clear is, we'll say this. So this is 0.8. Let's just say 0.7, right? 0.7. This would connect over here at 0.3. This would connect at 0. This would connect at 0.3. This would connect at 0. This would connect at 0.6. This would connect at 0.8. This would connect at 0. And there you go. So those are our connection costs. So basically, to traverse from here, 1 to 2, it would be a cost of 0.7. 2 to 3 would be a cost of 0. 3 to 4 would be a cost of 0. And 4 to 5 would be a cost of 0.8. Right? Makes sense? Now if we were to go the other way, 2 would take a cost of 0.3. So if you wanted to go from 2 to 1, that'd be a cost of 0.3. To go from 2 to 3, that would be a cost of 0. Or, well, actually, no, because we already drew this right here. To go from 3 to 2, this would be a cost of 0.3. Your water level had to be this high. To go from 4 to 3, this would have to be a cost of 0.6. And to go from 5 to 4, this would have to be a water cost of 0. Basically, I established these rules, and I had the idea that, oh, well, maybe we should represent the flow of water as its own tree, and then you would have to like dynamically add to the tree to represent the flow of water and stuff like that. But I decided for some reason not to continue going through that route, because I thought I would be able to do this without I thought I'd be able to do this by straight traversing the tree. with a graph. But that is not the case. It was actually, you have to build the tree, which represents the flow of water. So, my original idea that we had. So, how does this work? Well, what we can do is we can build our starter tree, and we can just look at this map for this example. Like, I don't even want to look at the actual map. We can just look at this. We have our source. What we'll do is we'll create what's called a source node. So the source node basically will pump water into like whatever other node needs to go to, right? That's all it does. Now you can begin the simulation by attaching a cell to it. For our case, we'll attach 2. So we can attach 2 to it. 2 gets attached to the source node, so water will traverse into here. Now we can see we're at 2. Where can we go? And this can kind of tie into the cases we established earlier, which is when should we fill up a cell? When it either has no neighbors or its water level is less than the minimum connection point. And we can see the minimum connection point is 0, which basically says, oh fuck, we have to go somewhere because our water level is equal or greater than or equal to it. So 2 basically is like, okay, well, water can't actually sit in this cell yet, it has to go to 3. So 2 will connect to 3. So we'll draw this, because this is the graph of the flow of water. See the source, we go to 2, and we go to 3. Now 3, we use the same rules. We see that 3 has to go to 0, which is 4, so 3 goes to 4. Now, can 4 go anywhere? Well, it can't go this way, it can't go back, and it can't go forward, because if it wanted to go anywhere, the minimum is 0.6. So it can't go anywhere. Which means we have to fill up 4. So what we do is we begin filling up 4 until it reaches another it reaches a connection point. So we start filling this up. Then we can see that once we hit 0.6, we have to go back somewhere. But it turns out we're just basically going back to this parent, and this parent basically says, okay, we're gonna get into a cycle here because now we're going from we have to go, the water has to go up, but then the water has to go out, and we get into the cycle which we found earlier. Well, if we ever have this case where the water level is equal to the parent, what we can do is assign this node to its grandparent. So basically that means, okay, so once that reaches 0.6, we're gonna traverse and we're gonna add it to here. And I'll say water level equals to 0.6. So once water level is equal to 0.6, effectively what's happening is 2 is, like, you can effectively think we've combined it. These are now combined in the tree. They're at the same level. So they're dependent, both these nodes are dependent on 2. So we check this condition, and basically what we do is we always update the leaf nodes. So we can see that 3 is now a leaf node because it doesn't have this connection point anymore, and 4 is a leaf node, so we can just continue updating these. So now 2, 3, and 4 will begin filling with water. Which then they would fill up to, like, I'll mark this in purple, they would fill up to, like, this point. To where 4 will match with 5. Now we can see 4 can go somewhere now. 4 can go to another place. It can go to 5. So now what's going to happen is 5 is now a child of 4. However, we can see from earlier that there's a cycle here where we go 0.8 to 0, 0.8 to 0, 0.8 to 0. Where they kind of go back on itself, where 5 can now reach its parent. Because at its current level, water level, once it can reach its parent, you're in a cycle. Since this happens, what we can say is, okay, well actually, 5 is not a child of 4, it's a child of 2. Because technically, they're all at the same level here. Which, that all depends on what 2 is doing, because water is flowing the least resistant direction, so since 2 is here, water is going to go down here, and since they're all at the same level, we can just start filling. So now that 2 is here, these are all leaf nodes, so we can all begin to fill them up at the same time. what's going to happen is by the time it reaches around here, which is 0.3, 2, now these are all at the same level. So basically what happened here is 3 can now return to its parent. 4 is not technically like an original child of 2, but we'll have to think about that, how we want to implement it. But what's happening here is they've all reached a level where they can meet at this point. And then we can see that there's a cycle, right? So they meet at this point where it can go back to where it needs to return, right? So basically, we can move these up to the source node, where now what it's going to look like is where we can move all of these. 3 goes here, 4 goes here, and 5 goes here. And now we can, since these are all leaf nodes, we can fill up all these nodes equally. And then eventually what's going to happen at the light blue line is basically 4 is going to get filled up. And once 4 gets completely filled up, we can, and there's no other parent that I can connect to, right? So there's no top one, right? We can kill 4, because we don't need to update anymore. 4 is now gone. But let me change this to light purple. Once we get up to here, which is like kind of like this water level, we can see that we're having a new dependence, which is 1, which depends on 2. So 2 basically goes down to right here, which is 1. So 1 gets added right here. Now, what should happen here is 1 should be the only one being filled up. Wait, 1 second. How does this work in real life? Because this guy, okay. One second. I have a solution, right? But I need to think. Because if this is true in real life, then this would make this problem a lot easier. What I'm thinking is does 2, if we reach this water level for all the things, because they're all rising, if we reach this water level, then does all the water go into 1, or does it still keep pumping into 3, 4, and 5? That's the question. Because if that's the case, where it would, if we still reach at this level, 1, 3, and we still have to pump 3, 4, and 5, then the solution is as simple as just saying update all the leaf nodes. If it's not, and we say, okay, well, we can only pump into 1, then the solution gets technically a little bit more complicated. But I don't know. Is that the case? Is that how it works in... Let me look this up. How do cells fill up with water when pumping? Okay, I don't care about like the biological part. I just want to know how does it work. Okay. You know what? Yeah, that makes more sense. That makes more sense if it affects all the cells still. Like, that doesn't make sense that it would only follow one path. So this actually makes our problem a lot simpler. Basically, what's going to happen here is what I decided is that these other nodes, if we were to have this get affected, this doesn't matter. We would still begin to fill up this water, which will be represented by this fucking gray. This will begin to fill up, while also these will still begin to fill up at the same time. Because that just makes sense, to me at least. So if you're dumping water, not dumping, but pumping water into a system, say you had a breach in your submarine or whatever, and there's water coming in, water is going to flow anywhere it can flow. So it's going to go here, it's going to go through here, it's going to go through here, it's going to go up, and it's going to try to go through here, and then it's going to try to go up, but it can't, so it's going to go up here, it's going to fill up all this, and then it's also going to try and flow down here. Technically, this one should also rise too. Like, this one should also rise too at the same time. But, I mean, we can implement that through code. So basically, this problem just boils down to looking at the leaf nodes. So, right now, we can see that 3, 4, or 3 and 5, because 4 is already filled, we don't really care. 3 and 5, they're leaf nodes, so we can just update them. 1 is also a leaf node, so we can update that one. And then 2 would be the only one that isn't updated. And then, as you run that simulation, what would happen is, over time, 3 would be the first to fill up, so 3 would be the first one to go. Once 3 fills up, I think we'll just say 5 fills up too. 1 will meet this matching point they have. Once 1 meets this matching point, then it'll get reassigned to like this, and now 1 and 2 are both leaf nodes. Once 1 fills up all the way, because it would fill up before 2, 1 would get deleted, and then 2 would finish it off right up here, and then 2 is gone. And then once all your source nodes are gone, you only are left with the source node. You can call an end to the simulation. There you go. So basically, the simulation just boils down to constructing a tree, which represents the flow of water, and only pumping or like updating cells that are leaf nodes. So only updating the leaf nodes of the tree. And to tell when you should merge and update your tree is if they reach this matching point, then you should assign it up, and then assign a child if, like, per se, you reach another connection point. So if you reach a connection point, assign a child to yourself, but if you reach your returning point, assign yourself to your grandparent. That's kind of basically the simulation. Let me do one more example. Okay, so you have this parent cell, you have this cell, you'll have this cell, and we'll have this cell. We'll have these 2 cells. 2. Boom. 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 There you go. So, to traverse here, you'd have 0. To traverse here, you have 0. To get back up, you'd have 0.6. To get back up, you have 0.7. 0, 0.2. To get back up, you need 0.9. To get back up, you need 0.7. Let's just say that. Let's make this our source node. This one our source node, and let's mark them. 1, 2, 3, 4, and 5. So this is the way it would work. You get your source node, and you attach it to your starting node, which is for us 2. Once we attach this to 2, 2 has 2 parents I can go to instantly. I can go to 1 and I can go to 3. So you have 1, and you go to 3. Well, can 3 go anywhere? Yes, 3 can instantly go to 4. So 3 can instantly, I'll draw like this. 3 can instantly go to 4. Can 4 go anywhere? No. Can 1 go anywhere? No. So these are our final leaf nodes. Now, what you do is you start updating them. So you fill these two up at the same time. Since 1 meets at 0.6, this is the first one to level off with 2. And, so once, sorry, 1 second, I keep getting distracted. Once this has 0.6, this will be at 0.62. One and 2 will effectively become the same node. So this one will get connected to the source node. You get assigned its grandparent. So you get assigned up here. Now, here is an issue though. Which kind of ties into what I was actually thinking about earlier. Technically, if we were to say we can only update the leaf nodes, that would be wrong. Because at this current moment in the simulation, if we were to update only the leaf nodes, we would update 1 and 4. Problem is, you can't update 1 because you can't pump water in here because all the water is kind of going out through here. Right? I mean, technically, if you filled up 1... No, that's not how that works. God damn it. I should have, like... thought about this more. Because 1 shouldn't technically fill up. 1 should have to wait on 2. Let me see this simulation, this example. It was source, and then once 1 hit this, and then at the orange, or at the pink, you'd attach 2 here, and I mean these would all be at the 3 and 5 would be where were 3 and 5? Well, 3 and 5 would be attached to the source node directly. So, I mean, technically you'd be able to update it, but we may have to change the rules then for this to work. Because if we could change the rules where we say, okay, you can't update this until you can't update 1 until the original parent is satisfied, has no like children. But that can become an issue because yeah, 3 and 5 will get updated until 4 and 5 when they get updated until Okay, so the issue I'm battling on is when do I want to update a node? Do I want to update it as a leaf node, or do I want to update it? So here are the two cases. If it is a leaf node, right? Which this is a leaf node right here, this one. Or if it is a leaf node and the parent doesn't have any children greater, like it only has like the max depth, like they're on the same level basically, like it's at the deepest level. So this would be level 1, this would be level 2. Because basically what this is saying, okay, we have the source node. Can we update this leaf node 1? No. Why? Because this 3 exists. But if this 3 were to go away, then yeah, we would be able to update it no matter if the parent has more leaf nodes or not. But I'm more concerned is, does that work with our simulation? Would that rule give me the most optimal result? Because if we use that rule here, what would happen? If we use that rule here, 3, 4, and 5 wouldn't update once they meet this level. Once they reach this level, 3, 4, and 5 wouldn't update. Well, 4 is already full, technically, but 3 and 5 wouldn't update. They would have to wait on 1 to catch up. And then they would rise at the same rate. But I'm pretty sure when you would pump water into a system, they rise at different rates. Technically. But if we don't use that rule, we can have a case like this, where this would update while it really shouldn't. I think and this isn't really an issue, like this is just more of an issue of what do I want for this simulation. Chat for some help. Oh my god. I cannot use ChatGPT to save my life. No, stop. Here we go. This is a good example. There we go. What the fuck? How do I leave? Oops. Alright, how do I change the view so I can see? Okay. Yeah, but this is like doing fluid dynamics. It's not doing what I want. Okay, we'll just assume. We'll just do. All right, that's it. I'm done. I'm done. I'm done playing. We'll just do it this way. And if we don't like it, we can change it later. So, yeah, I think that is the best case. So, we can kind of get to coding here, because what we'll need is, for this solution to work, we'll need the structure map. So we will need a graph of the structure. So for example, 2, 1, 3, 4, and 5. And then we'll need a map of the structure, and then we'll need obviously data about where they meet and how they, and what happens. So we'll need this map structure, which basically tells us, okay, if we were to go to here, this would take us 0. If we were to go to here, this would take us 0. If we go from 3 to 5, this would take us 0.2. If we were going to go from 3 to 4, this would take us 0. And then we obviously need the returning information, which if we were to go up, this would take us 0.6. If we were to go up from here, this would take us 0.7. If we were to go up from here, this would take us 0.5. And then if we were to go up from here, this would take us 0.7. So this is our map information, or our map graph, right? Map. And then we'll have our, obviously, our fluid graph. So this will be our fluid. And then what we need to do is we need to pick a starting point, so we'll pick 2. And then from there, we can use this map information to build this fluid tree. And then once we have built the fluid tree, technically, we can just use both the map and fluid tree to just figure out what we should do in the simulation. So we'll have 2 graphs, or 2 trees. The fluid one is basically a tree, while the map is a graph. So we'll use a combination of these two to get the solution working. Alright, I'm back. This way. And we can get the coding. So So I think I might wipe all the progress we made, like all the code we wrote last stream, because this is kind of going to be at least a little unique. Oh, one second. I think I actually figured out how I want to do it. What I will say is that we won't update the deepest, but we'll update a leaf node if its parent doesn't have anything greater than it. If its parent doesn't have a deeper level than it. So, for example, in this case, 1 will update and 2 will update, obviously, but 1 will update. But if I add this down here, 1 will no longer update. However, 3 will update because it's right here, and then if I were to add 4, and then 3 would continue to update, and then if I were to add like this or whatever, then we wouldn't have to worry, because we only look at the parent, direct parent, we look down. And then if 4 were to have a child, obviously we wouldn't flow down here. 1 will still will no longer update. None of these will update because the situation. But if all these were to drop out, 1 and 2 wouldn't update because we would have 6 dependent on 7. But then once 7's gone, all these will update at the same time. That's kind of the approach I'm going with. So it's not the deepest, because technically what could happen is we could have like this, but we would want, you know, if I were to get rid of this, we would want 3 and 4 to update at the same time. But yeah, that's how it would work. I think that's the best way. So, alright, so what we're gonna need to code is a pretty fucking good, graph library. At least we need a good tree builder, and we need a good, hello? The hell? Oh, no, it's, no, it's true. Okay, so what are we gonna need? So for our map, we're gonna need a graph, which, you know, has edges, right? What is it called when you store information about an edge? Oh, edge, I'm an idiot. So it has edges, or has nodes, edges, with information, and it needs to be bidirectional, and it only needs to be built once. So, not very complicated, but it needs edges with information, it needs to be bidirectional, and it only needs to be built once. And it needs to be somewhat easy to traverse. However, for our fluid tree... Fuck, did I spell fluid right? No, I didn't. That's not how you spell fluid. It's fluid. For our fluid tree, we don't care about which direction, so it's just one direction. It's just basically an end tree, right? It's a generic tree. It's just an end tree. However, we need some helpful functions, like the ability to delete, obviously, swap to grandparent, and check parents max depth. We need these 3 functions. And each node of this, each node will store the following information. The node needs to know its current water level, or it just actually needs to know, who it, it just needs to know, which node it relates to in the tree. So it just needs to know which node it relates to in the tree. It needs to know its parent's maximum depth. It needs to be able to swap to its grandparent. And it needs the ability to delete. And obviously it needs the ability to add. Like, fucking obviously. Add. And then for this, you only need the ability to add. You don't need the ability to delete or nothing, because you're never going to be doing that. So these are our requirements. And, kind of get started. So, let's call this a map.py. And we'll just create a class called, no, not map, because map's a keyword, yeah. Class called map graph. Map graph. And for now, we can just export inits. And print created map graph. And then here, let's import map graph from map.py. Is this how you import in Python? I forget. Bro, just tell me how to import other Python files, please. Why am I getting so much shit? If I say map.py, does it yell at me? Does it want it like this? Does anyone know how to do this? I forgot. I normally don't input. Python's like my like scripting language. I never really use it to build like larger programs. Python module. Okay, so import map graph. Okay, and then can I just say map graph? Or I'll just say map. What the hell? Let me change this to map graph.py imports map graph. So from map graph imports map graph. There you go. That's how you do it. There you go. Nice. And let me show you my go. Okay. So we have our map graph. I'll just separate this into. I really need a pie cache. I'll separate this into a fluid tree. Yo. So we'll get the fluid tree in there. We'll just say class fluid tree. Oh, I forget that fuck, it's snake case here, bro. Map graph. It doesn't really matter technically because it's my code and no one's gonna watch it. Like no one's ever gonna use this, but I'll follow convention. Who cares? And here we'll do inits. Created. Go. Now from for map graph. Graph video. I don't know if it's really necessary to create all these extra files, but who really cares, to be honest? There you go. Now, we can sit here and we can focus on this. So, honestly, I can rename this to graph, and then I can rename this to tree, and then I can go down. Whoa, do not do that. I rename this to the tree, to the graph. We'll just do this instead. Import this. Import this. So we'll go down to here, and then we'll say map graph dot graph, and then we'll say dot tree. The reason why I'm doing that is because there's a lot more information that I'm gonna need to store. So in here, we're gonna need a class called a node. Right, and the tree basically just holds the nodes and does the functions on them. Print creating node. Go. Let's go to map graph. Now let's do the same exact thing. That's called node. Fine. And it's here. Print created graph or map node. There you go. Go to fluid. Created tree or fluid. Tree node. There you go. And we can have the context of that. We can jump down to here. Graph dot node. There you go. And then fluid tree dot node. So you have these two classes which you can use. Now, the first thing I want to tackle, which we've kind of already done, but I want to actually handle the creation of the map. So, we need a node. For now, the node will just store an ID, and we don't need to know its neighbor, it just needs to know its ID, its water level, because I will honestly store that in the map. It needs to know its starting water level, which means default equal to 0. But you can, like, I guess, it doesn't need a water level. Okay. It just needs to know its ID for now. Doesn't matter. Alright, and then we can just say self.id is equal to ID. And then we'll say self.water level. Or we can just go up here and just say water level equal to 0. There you go. Nice. So, creating map node. This ID. Nice. For now, that's all you need to store. Now we can go over to the graph, and we can create our basically kind of like our adjacent to this. So I do want to build that off rip. We're gonna need to know information about its connection. So our node can store its ID and its water level, but we're going to need to store information about its connection. So class called connection. Do I have to like create it as a class if I want to store extra features, or can I create it as like kind of like an object? Oh wait, here. Yeah, but I don't want to access it like that. It doesn't matter. Just create a class for it, who cares? Alright, so this is a connection. It needs to know the to or the from node, which and it needs to know the to node. It needs to know the forward cost, and it needs to know the backwards cost. So from node, to node, forward cost, backwards cost. So basically what that means is if you go here to here, yep, from node you gotta take that cost, the to node you gotta take that cost. Here we can say self.from node, obviously, self.to node, self.forward cost equal to forward cost. And then self.backwards cost. Backwards. I just call it backward cost. Who cares? Oh. Oops. Whatever. Backward cost. Is equal to backward cost. So you got the from node, from node, to node, forward cost, backwards cost. There you go. That's a connection. Now our graph will basically keep a our map will keep a. How did I do it over here? Set that graph, default dict, okay. Now, here's how, the question is, how do I want to actually store this information? Because I want it to be quick and easy to access, so obviously a map, right? I use a map where the key is the node, and then it returns to you the connections. I think I'll do that, and I could just access it from the to node. Alright, yeah, that's how I'll do it. So it will be the graph will basically how do I want to name this? Just say map underscore graph. Okay, so self.graph is equal to it. Oh, I need to import that at the top. Import from connections. Okay, right, or is it from collections import? Yeah, it's like that. Down here, see, dict of a list. Now, do we need any other information? I don't think so. And the list is basically a list of connections, but we doesn't need to know that. Now, what we can do. And then what we can also do is we can have a self.nodes, which is basically a map of nodes. It'll tie an ID to a node. So, I think I like this structure so far. We'll just call it a add node. And we'll take in just a node. For now, we'll just do stuff.nodes. At node.id equal to node. And we'll return a boolean, which basically determines if it was successful. So if self.nodes at node.id, or if like not node if not node, or node.id is less than 0, or self.node's ID exists, right? You should return false. Else what we can do is we can just return that, return true. Right, because we can say self.node is equal to node. Now we can do add edge. And basically we'll take the and then from ID to ID pool. We'll just say if from ID is equal to 2ID, or from ID is less than 0, or self.nodes dot or not self.nodes ID. Else you just say so basically what this is saying, which I don't know if I want to throw errors. Maybe what I'll do, how can I assert in Python? Can I just panic somehow? So I'd love it if I could I just say raise exception. Yeah, okay. Alright, that's what I'll do. So instead of doing like this Boolean bullshit, I'll just raise an exception, crash the program, because it doesn't really matter. I just need to know that I fucked up somewhere and why. So like this doesn't happen, but what I'll do is I'll say what is it, raise, or I just say raise exception, add edge ID, incoming yield invalid, either nodes do not exist or IDs. Go. Else we don't do fuck. Don't ever anything else. We'll just basically we'll create an exception. We'll just say add node. Node is null, or node or ID is less than 0, or node already exists. And I shouldn't really need that detailed error messages, because again, I am not making this like no one else is touching this code. It's not going to be that big of code, hopefully, so it should be fine. So I don't need to have like an error for every single type it is. I just need to know that an error happened and kind of roughly why it happened. So if I would say I'll just say I hate how map is a keyword, bro. Map graph. I just say map graph. I hate this shit. What should I call this? I'll just call it sim map. Sim map is equal to this. Sim tree is equal to that. There you go. Now, sim map dot add. Oh. This should be as a map graph. I don't like how I have no knowledge of what this is. Has no attribute graph. Oh, because I changed the name of it. That's why. I was like, what the hell? Why is my LSP not being it up? There you go. Add node. Now this should hopefully crash. Oh, it literally crashes because I didn't pass in a parameter. The node required me to do it. So we'll just pass in done. And there you go. Exception happens. Nice. So the exceptions work. Go back to the map graph. Or here, let's actually add a node. Node, which would be equal to 1. And literally just take this, paste it, and we should get an exception. Here, let me comment this out, raise that. Why did you fail there? This should be node, right? If not, what's wrong? Oh, do I have to say in? I can't index it directly? That's a little stupid. Thought I could index it directly. Is that the issue? Yeah, that was the issue. This is gonna be a lowercase, by the way. I don't know why I had it capitalized. It's gonna be it's there you go. Still working. Go to main. Now let's uncomment this line. If we get an exception, we do. So that is working. Now let's just add edge, okay? I'll basically say if not from ID in or not to ID. If they are, we need to store information about their connection point. What I could say is we could just pass in, honestly, we could just be like, pass in a connection argument. Do I want to store like the node itself, or do I want to store its ID? Pass by reference or pass by value when you pass in like complex objects? We'll do this. So we'll take that. Take those two. So you want to do is self. Now, to actually add the connection, you need to also check. Okay, well, we'll need to check if that connection like exists within our thing. So let's just say connect object is equal to connection. Now we'll take in, oh, you motherfucker. Maybe it won't be as simple as last time. Okay, well, let me work on this one then first. Fuck this. We'll just say, and then we'll say, well, these will throw exceptions if they fail, and then we'll say, here, connection object or con object is equal to connection. From node to node, forward cost, backward cost. And then what we'll say is, now I want to check, I do want to check and be like, okay, does this connection like object kind of exist? Do these? But what I'll have to do is I'll have to iterate over all your connections. What I could say is a node could have connections, and then when you add an edge, you just say, okay, hey node, turn on. I feel like I'm overcomplicating it at that point. Alright, so simple case, I just make a function. This will be this will be just taken from ID, and then a to ID, and then we'll just return a connection. Now, if not ID in nodes, self.nodes, I gotta pass it self.nodes. No, that doesn't exist. Else, what we can say, or self dot there you go. Node is anywhere. Now we'll just loop through. We'll say so for on in self.graph at from ID. If on dot, okay, now can I say, hey, this is going to be connection? Yes. For con dot to node equal to ID, return this connection. Oh, so we make it through the whole loop. Return just say node is non-graph or node no connections. Okay, so we should be able to get a connection just based off an ID. We'll basically say, we'll just say find connection. We'll rename this to if self.findConnection from node.id to the toNode.id. We'll raise an exception saying connection exists. Else we can make the connection. So we'll say new connection, and then what we'll say is, we'll actually go ahead and add it. So we'll say self.nodes or graph at toID equal to .append its new connection. There you go. Which this works, right? Now I could see an issue where, oh no, because the graph we don't have to worry about adding or deleting. So like this kind of functionality, we gotta make sure it's robust. We gotta make sure it's good like this. This is good. I shouldn't return an exception here. I'm just gonna honestly print it. Who cares? I don't need to know. I don't need it to crash. I do need to know. So you find a connection, just return none. I don't want it to really crash. And then add node, yeah, I do want it to crash because the only time we'll be adding node is when we're initializing the map. So obviously I would want it to crash. So now we add an edge. Now we can handle the case for this one. If self.findConnection from the toNode and the from ID raise, and I'll just take this and paste it here. There you go. And then else what we'll actually do is we'll just say new connection. We can honestly just go down here and then just yank that 12, paste. There you go, new connection. Hit that, and then we can kind of go up here, and we can delete this dots. Or actually, I'll just open it to ID, and we'll go here. And then we'll create a thing called find node itself, and we'll say ID. Let's return a node. Just if not self.graph ID. Return none. Else return graph ID. Or if ID not wait, what the, I don't believe this actually. 1 second. This should not crash, should it? Oh wow, gas crashes. That's so weird. I feel like it never crashed before. Whatever. So if not ID in self.graph. return self.nodes. I return else we're gonna return self.nodes. Here you go. Now for find connection, we just check if not. And then obviously we'll say from ID. Here we'll say alright, so boom, boom, boom. You know, we are taking the cost that this is taking a little bit, right? But it's at the benefit that this is going to be kind of robust at first. So 2node, which is equal to self.findNode 2id. 1node is equal to self.findNode ID. And then if not not 2node or not from node or 2node or 2id is equal to from ID, we can say we can raise this exception. And then we can check if that connection exists. If that connection exists, then great. Else we just say from node and then to node. Now we create that connection and then we append it to the graph. Go. So we have the add edge, we have the add edge VID, which is clean, and then we have the find node, and then we have the find connection, and then we have the add node. And I think that's all we kind of need, to be honest, for the graph. We just need really that. Obviously, we're gonna need the ability to traverse these nodes. But like this is more or less for the map building itself. Now we've built the map. So you have add node, add edge. There you go. So kind of all you really need to build the map itself. We haven't really worried about traversing it yet, but traversing it shouldn't be too hard. I think that's more or less up to the simulation to decide how it wants to do it. So. And we can comment it up just a little bit. Adds node nodes. Throw some little quick documentation up on this thing real quick, just in case I'm not able to finish it today and I can come back to it. Or maybe potentially any of you want to use this. Yo. So literally the same thing, but does it based off ID. Finds connection and returns connection object if found, else returns none. And then here it's finds node and returns node object, else returns none. There you go. Self-explanatory. So let's see if we can build a map real quick. Let's see how that goes. So in our sim map, we want to add a node, and we can kind of just do Honestly, dude, just taking an ID. I don't really care. We don't need to do all that shit. Just if ID is less than 0 or ID is in here, let's just do ID is equal to node of ID. It's like all you need. I don't really syntax creation. There you go. So instead of saying that, I can just say add node, sim map, add node, and just paste, and we can just say 3, 4, 5. So let's see, does this crash? No, it doesn't. So we create all these. Just print sim map dot nodes. What does that pronounce? That's out all our data. Now, do we have any connections though? Dots. Let's graph. No, we have no connections. And also, now that I think about it, I can rename this to not really graph, but connections. I'll just keep it graph, I guess. Never mind. No, I just keep it graph. Just keep it graph. So I don't have to rename everything, change it, doesn't matter. Alright. This works. So let's do simmap dot add edge via ID. I want to connect 1 and 2 together. To get to 2, we need a cost of 0. To get back, we need 0.8. Oh, fuck. I made these ints. We'll just do 80. We'll do on a scale from 0 to 100. You need a cost of 80 to get back. How to say node 2 have no connection? Oh yeah, because it's building. So we have 1 goes to 2. But we do need to know that we also need to tell I might have fucked this up. Okay, yeah, that's bad. So basically 1 to 2 from 2. This needs to be different. This, because it needs to be bidirectional. So this got fucked up in here. So we're saying to this new connection, and then we need to say self.graph. Oh wait, do we though? Yeah, we do. Yeah, we do. Oh, but now we're like appending all this extra data and shit. Honestly, might have overcomplicated this, because honestly we can just the connection just needs to store the cost that it takes. So we can just store a tuple of, and also these values don't change, so we can store a tuple of just where you're going and what's the cost. We don't need really this connection class anymore. So we can kind of get rid of that. This can just be a tuple of ints and ints. But it was nice knowing all that information, to be honest. I'm not gonna lie. Because I feel like if I had a connection, if I was looking at a specific spot, I could kind of do the logic. The reason why I kind of did that actually was if I could just kind of do the logic there. I don't have to like search, look at all my connections, then go find that one, find its connection. I can kind of just look. So if I can just kind of grab a node and be like, okay, if I want to go here to this node, it's going to cost me this one. If I want to get back, so I can do calculations, because it would be less searching, but just more memory saved and like duplicated memory. So actually, you know what? I'll keep it for now, because it doesn't really matter. It really doesn't. And then I can just say a new connection. From node, active cost, forward cost, and then from the from node ID, append the new connection. So it's not really like very readable, but it's just applying the index. And we can kind of just use this same logic here. Actually, I think about this as kind of a this is kind of a useless function. Because when, that's useless. Who cares? All right. So now, if I were to print this, this should be fixed. There you go. So you can go here, and then you can go here. I can just say at 0 dot 2 node, and then we can say at 0 dot 2 node. Oh yeah, because obviously it's not going to print out the ID of it. And then obviously, I don't know if I'm liking this kind of whatever. So I'll just do node int, and that should give me my types. Okay. So I think that's good. That might be a little bit stupid, but if it really does require rework, we can rework it. It really does not matter. So we have the ability to add connections. We can build a map. We can actually build our map now. So let's just build. So map creation is actually done. And we can kind of traverse it kind of simply. Honestly, I just wonder if it would be better if we did like a node. If like in our node class, we also just had an object or like an array which represents its connections and the cost. Like I really wonder if that would be better. Like if we just had like fucking connections, which is equal to a default dict of just fucking integer, which represents the cost, and all you have to say is connections to this node. What's the cost? That means, yeah, that is so much. Oh god, why that? Why'd I just implement all this stupid ass stuff, bro? This is so much better. Yeah, what? Connections, and then we just say define add connection. Just pass in the to ID. And then the cost. And then, obviously, since this is map building, we throw an exception. And then we just say, if... It doesn't really matter, honestly. We can just say, if toID in connections. Self, or I need to pass in self. Self. Connections. Else we just say self.connections from the toID is equal to this cost. That's simple. There you go, guys. So, what was my mistake there? How did I end up overcomplicating that? Well, I wanted like this. The reason why I made it like a class itself because I thought I would want all this other information, but I think it would be easier to just be like, okay, I give you this node, go here, because the to node is redundant. I mean, I guess the backwards cost is cool, but like if you just search it, it'll be fine. And this is a lot more simpler, in my opinion. Because here's what I'm thinking: if you're traversing the tree and you're adding all these nodes, you don't want to go and search through a node, and then you could. What do you think? Because if I'm giving you a node, you can get a list of its connections, and then it can tell you the forward cost and the backwards cost. And also, like, so I don't know, what is this extra complexity worth it? Because this is super simple. I don't know. I actually kind of think now, like looking into it just a little bit more, I kind of think that the extra complexity would be worth it, because if I'm just giving you a note, I don't have to do extra searches, and I don't have to verify that the node on the other side exists. Also here, I would have to say I would need reference to the other nodes, so I don't think this is the play. I think I could do something similar. I think we're fine. Then I can rename this data edge, to be honest. I think we're okay. I don't think I actually overcomplicated that at all. Actually, I do think I'm overcomplicating it, but I don't think I'm overcomplicating it that much. Now, if I print sim map dot find connection of 1, what are your connections? Oh, A to 2. Give me this connection. Oh. Yeah, I kind of broke out of my group right there because I was being stupid. Whoa, dot graph. Okay, so we have the connections. Why is this one not working? If not from ID in self graph. Wait, this is the opposite way around too, to be honest. This is from node. This should be from ID. Gotta pin this new connection. This should be to ID. Gotta pin this new connection. Yeah, that's how that should work. And we check if not from ID in self-type to return none, else for connection. Node 2 has no connections. From to 2. Oh, this is 2 node. This is 2 ID. And then why are you being weird? Oh, there you go. So you found it, so you found this, and then you print out the forward cost. So to get from 1 to 2, you would have to pay 0, but to get from 2 to 1, you would have to pay 80. Which is kind of helpful. And then if I were to say 2 to 1, what's the forward cost of that? Which it should be 80, and then what's the backward cost? Yeah. So the only thing I see going bad here is like the backward forward can get kind of confusing maybe, but I think we should be okay. Like this. So we can build a basic map. Alright, so we have the map done. Again, not working at the fastest of speeds, but who cares? Building tree. I only have like a little bit more time, so I think this stream I won't actually be able to finish the thing, but I will hopefully have all the data structures implemented, and then tomorrow we can implement the solution. I am not the fastest of programmers, I will admit that. Assuming that took that long. But I do code a little bit faster off stream, if I'm going to be completely honest here. For an hour of coding just to have this much done, very sad. Alright, so the fluid tree, this should be simple to implement though. You have a node? Well, the fluid tree just needs to know, oh yeah, well I can't get a little bit wonky. For now I'll just pass in an ID. And then we'll just say self. I actually kind of want to speed up here, so I don't really care about the so self.id. -1 by default. Okay. There you go. Well, really, I mean, this tree is just, you have a node, and you have how many connections. And that's all you're really storing. However, we do need to know its grandparent. That's like one unique feature about it is its grandparent. We need to know its grandparent. And we need to know its,
So I'm kind of thinking, how do I want to structure this? So we could have the store. I mean, we just need IDs, right? You don't need to store any information.
We just need IDs, which can just be a map, which represents connections, right? Again, connections are kind of technically one way, but it doesn't matter. So we just say, because with these connections, we don't need to know imports equal dick, or from collections import equal dick, right? Basically, what's going to happen here is we don't need to like know this is a list of ints, but here we don't need to know like any information about it. That's for the map to handle. This can just be a list of connections where the key is a node and the key gives you out other. However, we do want to know the parent though. That is something unique about this. So we can hold a connection, but we need to know which one is the parent. Now, how do I want to handle that? Do I want to do repeated searches, or do I want to store that directly within the node? Here, what I'll do for now is connections can just be a default dict of ints with parents equal int. Okay, so let me think about this. Basically, we just want an efficient way to know who the parent is and just kind of maneuver around that obstacle. And what we can do in the tree is we can be like, okay, we can have the parent ID. So when we say this, we say cell, we can say define init I want to think about this. Because the way I would do this personally is, if I was going to build like a tree, technically I could just have a map of connections which kind of represent the tree, but I really do want to know who the parent is. Now, with a parent node, now how can I check if it's a parent node? Efficient. Well, what I could say is, I could just find whatever, oh, bro, yeah, there we go. That would be simple. Parents. Default dict. So basically, to get your parent, you just need to plug in your ID, and then it'll just spit out your parent's ID. For connections, to see your connection, you plug in your ID, and then you can see out your connection's ID. That's simple. So you just store this information. Now in our tree, we kind of want these functions. We want to be able to add a node. Now, Paulo, of course I remember you. And the project is actually kind of going well. I don't think I'm gonna be able to finish it today because I'm only gonna be on for probably like a little bit longer. But we have a solution that works, which if you can go earlier in the stream when I explain it kind of poorly. Basically, we're gonna just build a tree which represents like how the fluid is flowing throughout the map, and then with those rules we can kind of move around nodes, and basically we are only filling up the tree's leaf nodes. So it's like, I'll explain this for you real quick. If we had a map, we could have a source node, and basically what happens is you can connect it to like a container you want to fill up. right? Which for our case would be 1. And then what's going to happen is 1 obviously goes different places. So the way this would look is we'd have this, and then we can say that this goes to here. And yeah, this would be simple. So for 1, we have 1 and 2. This takes a cost of 0. This takes a cost of 0.5, right? So what's going to happen here is in our map, like if this is our map, it would be 1 to go to 2. This is 0, but to go back, this is 0.5. So basically what happens is we add a source node, which is basically like the water node, which means we're pumping water into this node. And then we need to obviously flow to the, like, we need to take the easiest path from like last stream where we decided the edge cases. We go to the lowest path, which is 0. So we can go to 2. So in our tree, our fluid tree, this is called our fluid tree. This is called our fluid tree. S will go to 1, because obviously the fluid's going to 1, but then the fluid has to go somewhere else. It has to go to 0. So this is going to go to 2. But for 2 to get back to 0. To get back to 1, it needs a cost of 0.5. And right now it's at 0, right? Because there's no water in it. So it can't go anywhere. And since it can't go anywhere, that means we have to fill it up. So that means we have to fill it up. And it turns out that this is a leaf node. And this like situation is for all leaf nodes, because leaf nodes mean they have no children in your tree, and which basically means we've reached a dead end in our fluid, where our fluid can go. This is a dead end. We can't go anywhere else. So obviously that means our fluid has reached where it has to sit, and it starts filling up. And to combat the case of when they reach the same level, so when we have at 0.5 and this is at 0, right? They should rise at the same level. They should rise at the same time. We've discussed that, right? To ensure that they rise at the same time, once they match in level, which means once we have this cycle, because I don't know if you were there when I said that, oh, we have like a cycle that happens when they reach the same level. Once they hit a cycle, which basically means that this node can go back to its parent, we delete this node and we assign it to its grandparent, which means that this goes down to 2. So now these are both leaf nodes, and because 1 no longer has this connection, so this new tree looks like this. It's source, it goes to 1, and it goes to 2. Now both of these are leaf nodes, which means both of these will receive water. And then once, obviously, this fills up to its max, we'll delete it from the tree, which means it gets up to like this water level. And then we'll only have 1 left. And then 1 will fill up all the way, and then we'll have nothing left. And then once we have no nodes left on the source, it's just left with the source tree, we can say the simulation is ended. And an edge case that we could have is I forget. It's like this. So let me think. 0, 0, 0.5, 0.5. This is 0 and this is 0.5. Right, so if I were to dump water into this system, which these are 1, 2, 3, 4, we'd have the source, which gets attached to 2. Now where can 2 go? Well, 2 can go to 1, and 2 can go to 3, and then 3 goes to 4. Now, what should happen here is technically the water should rise right here. It should rise in this one, and it should rise in this one. And since these are both leaf nodes, that condition is satisfied. So that means both these will begin to start rising. And then these will match up at the same time. So once that happens, which I'll signify in darker blue, so once they like reach the same level, we can do the rule where we assign it to our grandparent. So since 1 matches to 2, they're basically the same thing. So this goes up to here. 1 or 4 goes to 3, which means it goes to here. Or well, it's already to 3, but it goes up to 2, which means it's the parent of 2, because it's going to. This is it's by the way. So with the trees, this is its parent, if we're looking at this node, and this would be its grandparent. Right, so we assign it to the grandparent, so it goes up to here. And now we can begin updating these. However, we have an issue where, and this is like another edge case I'm kind of dealing with, is technically right now, 1 should not update, because if these 2 were to update, like, because 1 is a leaf node, right? 1 is a leaf node attached to the source. However, and then you have 4 and 3. If we were to update, here, let me actually, sorry, I'm not like explaining this, but let me actually re-update this tree for you. So this is the updated tree. So you have source, you have 1, you have 2, and you have 4, and then I'll write it like this. You have 3, and then you have 4, right? Now you have this tree. Now, one edge case I'm having is technically 1 is a leaf node, but it shouldn't fill up because these 2 are connected. And all this water is going down to 3. So if this was to fill up but not 2, that would kind of break the simulation. So what I'm thinking is, if you're a leaf node of the source, right, your parent is the source node, you can't update unless you're at the minimum depth. And depth in a tree is basically how far down it goes. So at the source node, this would be depth 1 or 0. This would be depth 1, and this would be depth 2. And basically, if you're a leaf node of the source, you can only update if your depth is equal to 1, which basically means you have no other children. The source tree doesn't have any children down here. Because I think that will solve that like this issue. Because technically what we would do is we would update all leaf nodes. So if we did that without if we follow that rule, we would technically update this, and update this. But if you look, that's not how that works, right? Because 1 should not be included in this update pool. So I'm thinking that would be the correct solution to that. So if we use that rule and we say, okay, well, 1 shouldn't update because obviously these exist down here. So we would only update 3 and 4. So obviously 3 goes to here. By the time this happens, 4 is already filled up completely. So 4 gets filled up completely. And so that means we can get rid of 4. Now that these have matched, we can assign this to the parent, or to the grandparent. So we go up to the grandparent, which is this. So the new tree would look like this. Source, 1, 2, and 3. Now, since the source is at a depth of 1, it's like completely flat. Like this tree is at a depth of 1. We can update all of these at the same rate. So we can update these. I'll just draw it in pink. We can all update these children. And then they would get up to here. Of course, like 1 and 3 would drop out by this time, and then 2 would fill up all the way. And there you go. So that's the solution that I've come up with. And then obviously once 2 is done, 2 fills up, and you're just left with the source, you know your simulation's over and you can call it. So that's the solution. Yeah. And basically what you do is we have the map graph too. So like here, the map would look like 2 can go to 1 and it can go to 3, and then 3 can go to 4, right? And what you can do is you use this map and you use the fluid tree to like communicate each other. Yeah, trees are insane. And by the way, I gotta give my credit where credit's due. I have a friend who's like on who's on competitive programming team at my college, and he's really good with data structure and algorithms. So I actually had to consult him, and he helped me with it, and we worked out edge cases. I kind of knew that we should do this. I don't know if you were there in the stream, but I said that, oh, this is kind of like a tree problem where you have to build the tree. You have to build the tree with it. And as soon as he told me, oh yeah, so this is how it works, I was like, no way, dude, because I literally thought about building a tree. I can't believe I ditched that idea. And if I would have, because the problem I had last stream was I focused too hard on traversing the graph instead of building the tree. So I just focused too much on the wrong solution, and that's what happened. But he helped me out, and then we had some edge cases, which is like everything I'm talking about right now, those edge cases, and we were able to work those out together. But I mean, I'm glad I just didn't have to like look it up at least. But definitely an interesting problem. So I didn't even think about like, oh yeah, adding a grandparent, adding the source and swapping it. It's kind of cool. Yeah, I'm in my second year. Did you stick to Python for this whole thing, or have you sort of switched for certain things? Okay, so I'm just gonna assume that you're talking about Python for this project. Currently, yeah, I'm still in Python for this project because it's the easiest to code this in. And then I plan on switching if it gets lagged. Yeah. So I'll just do Python because it's easiest to like test out the product, and then I really want it to be able to handle like large scale simulations, and if it can't, I'll switch to like either Go or C++. So, yeah. And then right now I'm just building like the functionality for it. And I think what I'll do is at the end of this stream I'll just finish building the like constructors for everything. And then tomorrow we'll work on actually simulating the whole thing. Alright, sounds good. Hey, remember you can always watch back, and I'll definitely be live tomorrow. So I don't know what time. Maybe around 6 p.m. or 5 p.m. EST, or maybe in the afternoon. I don't know, but I'll see you around. Thanks for coming in, though. Yep. Alright, so for the fluid tree, you have a connection with your parents. You can just plug this in, plug that in. Now, when you add a node, you basically want the node ID, and you want the parent ID. And I will go up here and I will say the source. That's how you spell source, right? I'm not freaking out, right? Yeah. Jesus. The source ID is equal to -1. Okay, so that will be reserved to the source ID. And you just say connections. Oh, I gotta pass self. Put that here. Self.connections.append. Oh, you don't append any connections, but you do self. Oh no, yeah, you do. Self.connections at the parent ID is equal to or .append the node ID, and then self.parent at the node ID is equal to the parent ID. There you go. And then you have that source ID there. So you can add a node there, and that's kind of what we just need for now. So let me go through and like kind of run this real quick. So main.graph. I could kind of delete this code. Oh shit, he caught the lie. He caught the lie. And I took credit for the entire solution. I didn't tell anyone that you helped me at all. I said I came up with it myself. Yep. I'm a leech, I'm a leech. Nobody knows. One connects to one, so your source ID goes there, and then you have that parent. Nice. Okay, now we want to have the ability to delete a node. And then the node that you want to delete. Now, how do we want to handle deleting? Oh wait, this actually might be annoying now that I think about it. Oh wait, no it's not. So, okay, so when you delete, basically... What are the cases? Would you ever delete a node when it has children? I don't think so. Because the way it works is... Oh, no, you wouldn't. If it has valid children, then you can't delete. Because in our simulation, we have this, and then we would have like this. For any children to be satisfied, you would have to fill it up eventually, right? And so to delete this cell for this one to be full. Wait, no, that's not the case. Because this could fill up to here. Oh yeah, but then you would move it beforehand. So if I had 1, 2, and 3, technically it 1. Source 1, and then you go to 2. They fill up to this line. Once they fill up there, you go to here. Then these fill up together until they reach this, which then gives you 3. But since they're at the same level already, this gets reverted up to here. Because they're at the same level already, and you raise them together, which then would kill 2, and this would follow up to this line, which would kill 1, and then 3 would be the finished one. So I don't think you would ever delete a node you would never delete a node itself until it has no children. So we don't really have to worry about this. Like, we don't have to worry about shifting around the children. However, we do want to worry about swapping with the grandparents. So I will actually make that swap grandparents. And then you pass in the node you want to swap with this. Well, you swap with his grandparent, and then also, if you were to swap with his grandparent, would you only swap when it also is a leaf node? Yeah, because you'd be filling that up, and then once you reach this like connection point, then you can swap. So it would be a leaf node itself. Well, I was just more concerned for like I didn't want to like lose track of other nodes. Swapping with the grandparent. Yeah, I figured it out. So basically, here's the rule. For now, it's only leaf nodes, right? What we had was it was only leaf nodes, so technically 1 and 3 would get filled here. But I changed it where it was only leaf nodes that get filled. But if you were a leaf node of the source node, you wouldn't be able to get filled unless basically the depth of the tree was at 1, which means there's no other children. And I found like a bunch of cases that did that. So you fill up all the leaf nodes unless your parent is the source node. And then if your parent's the source node, you can only get filled once all the other children below you have gone away. And I think I have like the literal edge case that I discussed up here. Yeah, up here. Like I have like if you were to map out this one, that like situation plays out. No, it's not the deepest leaf nodes, because if you had 4, 5, technically at this iteration of the simulation, 3 would get updated. 3 would get updated and 5 would get updated. But 1 wouldn't, because it's a parent of the source node, so it has to wait until it's there's no other children below it. That's like the only case. So it's like the way it works is update leaf nodes. But if your parent is the source node, do not update unless the tree's depth is 1. These are the cases. And then if you want, I can draw out that map I drew earlier, so I can explain it if that doesn't make any sense. think what you should actually do is just whenever you swap a node to be a child of its grandparent, you should add a dummy child to that node. Well, I mean, I mean, oh god, I gotta end stream. Well, would our original solution work though? Wouldn't our original solution work? A dummy child? A dummy child. Goes to 1, which goes to 3, which goes to 4. But it can't follow a sibling if the sibling doesn't get water. Sibling isn't a leaf node. Oh my god, I see what you're saying. Okay. So for this case, you have a source, goes down to here, water goes down to here, water will go down to here. What's actually getting filled is this, right? Wait, I think I get what you're saying. So what you do is you add a dummy child until the siblings are all leaf nodes. Wait, where would I add the dummy child to? Like when I swap? So do I still perform the swap but still add the dummy child? Okay, so once I can fill this one up, then once they can connect, they share the same state. Then once this fills up, these can connect so they share the same state. But since this one can't take water, these two can, so these two update. Well, okay, so what does the dummy thing do? What's the point? Because if I'm still performing the swap, what's the point of adding a dummy value? Because here's what I'm thinking, not that you say it, but I don't know if this is more efficient than swapping. Is technically this is pumping, right? This doesn't take any water. This stays like no water flow, right? This is taking in water, so this gets water, right? This gets no water, but this gets water. And then once these two match, once they can equal each other, it can take the state of the parent. Oh wait, no, that breaks in this case. Wait, unless Wait, yo, wait, I think I just figured out something. What if you just build this fluid tree, right? The leaf nodes get water, right? But the parent isn't allowed to get water until all the other leaf nodes... Oh, wait, that doesn't make sense, because... No, never mind, that doesn't make sense. That's stupid. Because that could just go up. List of rectangles for each node. Oh, what? Yeah, so you could just... Okay. So, okay. Well, here's what I'll do. I was gonna end the stream anyways, and I'll hop off. When you get a chance, we'll hop on call. Instead of swapping to the grandparent, just add the rectangle to the parent. So if I have source 1, 2. Wait, so how should this tree be formed? So should the tree be formed in the same way? Where you start off with the source, you go to 2, you go to 1, you go to 3, and then you go to 4. 4 has a list of just one rectangle, which is itself. What would this list be? Nothing? Or would it just be 3? Or what would happen? This would be a list of 1. So 1 and 4 get water here, yeah. Just 3. Okay, and this would be just 2. Okay. Now what would happen? So if 4 was to fill up where they can match, what should happen? Say this needs to get swapped. What should happen? Oof. Yeah, I think that's clean. Because once this fills up to match, these two are here, but this is dependent on this one, so it can't update. Wait, yeah, that's clean. I think that's clean. Does that work for every... Do you know if that works for every case? I think it does. That's actually clean. That fixes the problem where it's bad. So now you literally just do only leaf nodes. Oh, not... Wait, that's actually so... And that's so much simpler. Oh, why didn't we think of that before? You motherfucker. Why did you only think about that now? Wait, that's so much easier to implement too. You fuck. Why did you give me the complicated one first? Yeah, well, I mean, I didn't implement much of the tree code yet. I only have implemented all of the graph stuff, so it's fine. So we're chilling. So, well, okay, that. Oh, okay, that makes sense. It's actually way easier to implement now. So I guess I'll do that off stream, and then next stream we can actually design the simulation. Or maybe I'll just keep doing it on stream. I don't know. But I have ran out of time. No, bro, no, not 2 more hours. Okay, well, let me go to the bathroom. Let me refill my water, and then let me ask you this. You make a good point, okay? You make a really good point. Give me 1 second, guys. Alright. I talked to the boss. We only get like 30 minutes max of more stream. But I will try to implement as much as I can those 30 minutes. Because then I want to take a break. To do other stuff. Like eat dinner. Not starve to death. Alright. Hey, don't say what time. What do you mean what? We have 30 minutes of more stream. It's the grind has been the 3 hours you weren't here. The grind was the 3 hours you weren't here. I mean, I can, but I'm not gonna stop a stream and start it on the same day. What's the point of that? Alright, here we go. Nope. Bro, I can't, bro. You gotta understand that. You gotta come to accept that. Okay. Just gonna update itself at first. Well, then I got 20 minutes. Alright, I'm gonna finish this, and we're locking in. I'm gonna speedrun this. I don't care how clean it's implemented. Alright, good luck. Good luck with that. Alright. Boom. Set events. Set events. Bam, bam, bam. Bam, bam. 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 Bam, bam. Alright, delete node. If we're deleting a node, basically, you just take self.connections. No, I can do that. No, no, no. No, no, no. I can do that. Can't I do that? Oops. What the hell? Oh, yeah, you're right. Depressing. I thought I could pass it as a type. I do it with my list. No, no, no. You're right. Alright, first, they always update their cells. Parents, if you delete a node, what do we need to clear out? We need to clear out... Let's say delete. Basically, what's going to happen is... combine two sets together again. Updates. Okay, so first step is set or add parents. Add updates to parents. So parents ID. Parent ID is equal to parents self dot parents at node ID. Then we do connections or self dot connections at parent ID dot remove node ID. Then we say self dot dot updates at parent ID plus equals self dot updates at node ID, and then we can just say self connections. Wait, what'd you say? By the way, some things changed slightly. When a rectangle is full, you can just delete the node. You can't just delete the node. You can only delete the value. And if this, oh yeah. I can't. How do I union? Union sets in Python. Oh, I have to use the union thing? That's stupid. What is it? Dot union. Boom, boom. Then self dot connections. How do I delete out of a map? Oh. I'll just say dot union. Look, it's side label. It's easier to read. Wait. What's wrong? What's wrong? Oh, I just said, I'll just do union because it reads better. Connections at... Oops. Alright. I'll just do that then. Not parent ID, but, self dot updates at node ID. Boom. There you go. Okay, so print that, run it. So default dict goes down to that connections at negative at the fluid tree dot source ID. What are its connections? It can go to 1. So it goes to node 1, and then you just check if it's a leaf node. And then you can check if it's a leaf node by just checking if the connections are empty. Okay, so now if I were to say simtree dot delete leaf, and I say number 1, what will happen? Oh, it crashed. Self.connections, no ID. And not delete from default dict like that. Delete installation. Oh, this raised an exception. Oh. Wait, so why is this crashing? Self.connections, node ID. Oh, because that doesn't exist. Okay, so but this is always the case. This is not. Because oh wait, since it's a leaf node, you don't need to do this because I'll have no. Well, no, because wait, do I even need to do this? I don't even know. I think I'm overcomplicating it. You get an empty set, and then if you get an empty set, that means you're done for. So let me do simtree.add node 2, which goes to 1. Then simtree.add node 3, which goes to 1. Now print that. Okay. Now print at 1. Okay, so you go to 2 and 3. So let me do this, but let me do simtree.delete leaf of 3. So you get 2. Then let me delete leaf of 1. Or not 1. What is it? 2? Let me delete 2. So you get nothing. And then basically we should just be able to say, oh, I could also have some error check right here. If self.connections, or here, if node in connections, I'll just say if node in self.connections and self.connections at node ID unequal empty set, check if set is empty in Python. What is the cleanest way to do that? It's none, yeah, the none statement. right? Wait, no, it's not. I'll just do length. That'll be the simplest. If length of this is greater than 0, which means it has connections, fucking print can't not a leaf node. I'll just throw an exception. Raise exception leaf node because it holds connections. However, we'll get the parent. We'll get the parent ID. We'll remove it from its connections. We'll add its updates, and then if it's the case, we'll delete that. There you go. So with that edge case, if I say 1 instead of 3, I should get an exception because I can't delete that because it's not a leaf node. But if I go delete leaf and I say 1, then it should delete. Yes, nice. And then I can say fluid tree.source ID. And then honestly, just pass it 1, delete, paste, 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 paste. There you go. So you get 2, 3, remove 2, get that, you get fucking nothing, and then we can say fluid tree dot source ID. Do none, but then if I take that, it's here, it should have 1. Alright, so that's the leaf nodes deleted. Now let's print out the responsibilities. I'll just say dev node updates. And just give me a node ID. And just return a set. Whoa, what the fuck? This is. And then just return self.updates at node ID. Okay, so now I can see. Okay, what is simtree dot? What the fuck is this? Oh, simtree dot updates, and then we'll just say ID for 1. Okay, so what does ID 1 update? It updates 1. Now, if I were to, and then 3 would obviously update 3, correct? Yes. So 1, at this case, 1 will update here. And then after you delete 3, it should update 1 and 3. And then if you delete 2, it should delete 1, 2, and 3. Nice. Very clean. And then if I were to do that, I can say print simtree.updates at... I don't think source ID is in here, right? So I'd have to say fluid tree.source ID. Fluid tree, that source ID is there. Honestly, I could just say this prints, deletes. So you got 1, which updates 2, which updates 3. You delete 3. Okay, 1 and 3 are required in this. 2 is still a leaf node, and there you go. Now we can just check if it's a leaf node, and check is leaf. Pass in the self.node ID. Turn a bool. If node be in self.connections and length of self.connections at node ID is greater than 0 or false, else return true. Basically says if that's in here and sets return true. Okay, so then I can just honestly replace this with just is leaf or not is leaf or self that is leaf of node ID. Now that should all work still. And then if I were to try to delete leaf of 1, I should crash. Let's get that conditions right. Okay, so we can check if it's a leaf, we can check if we delete the leaf, and then we update its responsibilities. So the sim tree is basically done. So that's pretty easy. So you get the connections, you get the parents, you get the updates. So when you delete the leaf, you give the updates to the parents. You check the node, you can add nodes, and then you can is it a leaf? And then like what you can update. But like this is kind of a useless function, I'm not gonna lie, so I'll just delete this. Alright. Now. This edge is a little complicated, I won't lie. But I think we'll be okay. So we have this, we have the node which represents the literally all it does is represents how full it is. So I honestly think, and there's nothing else I really want to state, I can honestly just merge this into a just like a fucking dictionary here where self.node is just make this an int. Like, this doesn't need to be a whole class. Like, this can just be an int. Yeah, no, this does not need to be an int a class anymore. So I can just remove this and make it a... Yeah. That does need to be a class for sure. So this can just be turned to ints, right? That's it. Self.nodes is equal to, if we add a node, we just set it to 0. And then here I'll just say nodes and then water levels. Yeah, I'll just call it water levels to be honest. And then I'll just say dot. No, I'll just keep it nodes, whatever, nodes. And if I ever want to update, I can. So, and then I'll just make this a default water level to 0. So it makes sense. Default water level 0 or dot nodes. Default water level. Add an edge. Just do that. This find node shit. So what am I doing? You get a from ID and to ID. Again, this connection just needs to be an integer now, right? So we don't have to do any of this shit. But we can check, and this doesn't need to be a thing. If not ID in self.nodes or not to ID in self.nodes, raise exception saying nodes do not exist, and then here I can just say this. And then connection ID is this. Okay, so when you make a connection, this just needs to be from ID to ID. This just needs to be from to ID to from ID. There you go. Append a new connection. You go there. You go there. There you go. Find graph. Find connection. So that still should all work. Well, let's do a sim map, and we'll just I guess print sim map dot nodes. So that node is at water level 0. Sim map dot add node 2. Okay, and then let's do sim map dot add edge from 1 to 2, which is 0 to 80. And then let's print a sim map dot find connection from 1 to 2 dot forward cost. Okay, and now is the issue down here, which is if not from ID and graph, There's no connections. For connection dot from ID. Now again, this graph contains that, which, and these connections just change. Con.to node. And then maybe I'll just change this to node to ID. Should I change it to ID or to node ID? I'll just change it to, just keep it from to node. There you go. That's simpler. Now this should work. There you go. Node 2 doesn't have any connections. I don't care if it doesn't have any connections. Don't give a fuck. 1, 2 takes a cost of 0. And then what's the backward cost of that? The backward cost would be 80. There you go. So now you have the simulation rules. Now you actually have to, you have all of the structure to do it. Now that was really easy to implement, now that I realized that this is much simpler, the fluid tree was very easy with that new solution. Now, we just need to actually simulate the fucking thing. So we have all the tools to do it. Now, we gotta simulate it. So let me build a basic map, which will just be one node. SimTree dot add node, which is the starting node. 1. The parent is the SimTree dot source. I'll just do SimTree dot start. Or when you create the SimTree, just do just pass in the starting node. Yeah, and then you can just say here you can just say self.add node, starting node to source ID. There you go. So I can say when I create the SimTree, I can just start it at node 1. And then the map can go to simmap.add node 1. Yep, so now you have the print SimTree dot updates. So you have 1 which updates 1, and then you have a SimTree dot connections. So -1 goes to 1, 1. No, that's it, yeah. Go. So we have the SimTree, now we need to traverse it. So how do I want to do this? Well, actually, I don't really care about the starting node. Let's just start from the source and kind of work our way down. And we can just do that through, let's just do a DFS on this biatch. Let's just do a DFS. And then, root or node per node. Now, here we go. Basically, what we're gonna do is let's just search the entire thing. How would I write this DFS? Well, if SimTree dot connections at current mode, I'll let you make a helper function that just says has connections. Is that a thing? How do I want to simulate this? So we can visit every node. We're gonna say we can return. Right? Else we want to print the current node we're at. Sim map per dot nodes at per node. Then we want to run DFS for con in simtree dot connections at per node. Oh well, we don't need to do this. We can just, it does it for us right here. We can just say DFS connection. Not really DFS. Print, or just call DFS on sim map dots source. Oh, not sim map. Sim tree dot source dots. What the fuck? It should be in it. Source node. The hell? Oh no, it's fluid tree dot source node. What's it? It crashed because this is not a thing. So we'll just start it at 1. Who cares? Gives you 1, it gives you level 0. Alright. Sim map node 2. Give me this. Here's your object. 4, and then I'll just say size, make it 10. Nodes 5. 4i range of nodes. Then map dot add node. I plus 1. There you go, buddy. And start it at 1. Okay. Now I need to add the edges. So sim map. Actually, the edges don't matter because right now I'm just doing this. So fluid tree dot or sim tree, I call it, dot add node. So 2 will be a parent, will be a child of 1. 3 will be a child of 1, and 3 or 4 will be a child of 3. You don't care about the connections. It's just 1 goes to 2, goes to 3, goes to 4, and then we can print out is self dot or symmetry is leaf. Then we can pass in the per node. Is this node a leaf? These two are the ones we would have to update, which makes sense. I mean, honestly, do I even need to like do a DFS, or do I just need to literally just traverse the leaf nodes? Because I can already know what leaf nodes are. I can just fetch all leaf nodes by searching and returning a list of all the leaf nodes. Like, I don't even have to do this like DFS shit. I can just literally just say I can just make a function called get leaf nodes. Get leaves. return a list. And 4, oh, well, technically, do I even give a fuck? I don't care. What can tell me how many leaves I have? I can just traverse updates or key eval in updates. French key eval actually. I forget which one comes first. Oh, you crashed. Alright. And then I can just return this. Return K if self.is leaf for K. Or this. Oh, this is worded the wrong way. Boom. Bam. 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 No! You fuck. Oh, is leaf. There you go. Print get leaves. So you get 2 and 4. 2 and 4 are your leaves. And then if I were to sim_tree dot delete 4, then if I were to print get leaves, would I have 1 and 3? I would. And then if I were to delete 3, and then I would get 2, and then if I were to delete 2, would I get 1? I fucking would. And then if I were to delete 1, would I get -1? There you go. So I don't even need this. Sorry. And then I can kind of simulate it by saying while sim_tree dot get leaves. Yeah. Alright, so we have this. We have this. Now, we have 5 nodes. Let's make the simplest case actually. Let's just make 1 node. And for our case, let's just have 1 tree. And let's just say sim_tree dot get leaves. We only have 1. Get 1. Now, what do we have to check? So I'll say leaves or leaves this while leaves and leaves at 0 does not equal -1. Because there's no way we can multiple leaves, but while leaves exist, no, I'm not DFSing it for leaf nodes. Chill. I don't think I am, at least. No. Okay, what do we need to do? What do we need to do? We need to check. Yeah. You just loop through all the keys of every single node in the thing. You just check, and then if you just check if it has any connections. While I'm sitting here and he's reading that, I'll just key in. That updates. Oh, actually, no, I like that. Well, how would you find it? Yeah, it is, but like, is there actually a faster way to get on leaf nodes? Or to get only leaf nodes? Have I never known this? Yeah, you're right. Let's do that. I was actually thinking about that, but I was like, nah. Alright. Okay, so how do I know? Okay, the parent node. Blah 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 blah. Okay, so you say the parent ID. Oh, well, every time you add a node, it's gonna be a leaf node at first, right? Yeah, every time you add a node, it's gonna be a leaf node. Yeah, that's literally what I was thinking. Then self.leafs.add a node ID. Because every time you add, it's gonna be a leaf. There you go. Get leaves. Should I just return the set or should I just return a list? Click cast? I don't even know. Return if node ID and self.leaves. Just return. There you go. There you go. There you go. Let me actually run this again, make sure everything's working. That's not cast. Should I even return it as that? It doesn't even matter. No, it doesn't. It does not matter. I don't think it matters. So I would just do just say while SymTree leaves and -1 not and -1 in SymTree. Oh, wait, one second. I do want to wait. One second. Let me test this though. Blah blah blah. Print SymTree.leaves. SymTree.remove. Delete leaf 1 print SymTree leaves empty set. Okay, so I can just say we have that. Let me do 2 goes to 1. the least would be 2. And then if I delete 2, this would be empty set because I'm not updating this. So when you delete a leaf, you just need to check up here. So you get the parent ID, connections, bam, bam. Delete update, you remove that, and then you say if length of self.connections of parent ID is equal to 0 leaves. You'll say self.leaves.add parent ID. So you add the parent back into the tree. It's a leaf node. There you go. And then delete 1. There you go. So while simtree dot leaves and simtree dot leaves and -1 not and -1 in this. Run the simulation. Okay. What's wrong, buddy? Why'd you freak out on me? Why did you freak out on me? Oh. Print leaf. So you get 2 and okay, yeah. So can't I delete 2? Simtree dot remove dot delete leaf. Good. Why did this crash? Okay, so simtree. Okay, and then if I delete 1. Gives me -1. And then I bet if I try to delete -1. It will crash. Yeah, okay, that's why it's crashing. Weird, I don't know. And I'll say if -1 in simtree.leaves break. I just and can't I just say simtree dot leaf? What the fuck? What is going on, bro? Like, I shouldn't have to add that because the uppercase handle. Like, what the fuck is going on? Oh my god. No. One iteration. Print the leaves. For each leaf, you delete the leaf. Oh. Oh. Is it because it's updating that, like, thing, so it's gonna freak the fuck out and it's gonna try to delete itself? Okay. 2 iterations? Okay, so on the second iteration, it killed itself. What the fuck? Is it because I'm editing the same like object? Oh, I can't? Oh shit. I didn't know that. The hell? Yeah. That's what I was about to say. Wait, can I do this while loop condition still? And can I still do this while loop condition, or will it freak out? Okay, no, I won't. I got it. Okay, so boom, right here. It's so basically we know the simulation ends when the -1. Oh wait. Because once source ID becomes a leaf, we know that we've done all the nodes. Alright. Now we just need to implement the logic. Once we implement the logic, we'll be done. Go. We can get the current water level. Now we can loop through the conditions. Now how do I want to do this? Do I want to go through every single leaf node? Okay, yeah, so what I'll have to do is I'll iterate this twice because I'll need the final leaf nodes to update. Okay, yeah. So. Oh wait, what am I doing, bro? Just, I don't really care that much. Stop. Just make it work. Make it work. Don't make it fancy. Okay, so if the water level is greater than 100, we should remove the leaf. Okay. And then for now, we'll just say everything's at 50. Just makes sense. But what we'll do is now we need to look through all the connections. They might be able to make that. Well, first, let's just do this. So if the water level is greater than 100, delete the leaf unless don't do anything. For each leaf, do this, and then we just, for every iteration, we can print out the, let's just do map. Or here, every iteration, let's just, print, sim app dot, nodes. Why did you get map? The fuck? Oh, because it's more nodes then. So you got these 3 nodes, you get 2 goes to 50, 2 goes to 100, 100 fills up. Sim nodes, leaf plus water rate. Okay, so I should update first and then I should check. So I should update all the leaves, check their condition, and then I think that's like the standard update loop. Yeah, so 50, 100, 150, right? Whatever, 50, 100, and then it finishes. Greater than or equal to. So basic filling. Here, I'll just print down here, and then I'll print a done, and then I'll print a sim map dots. There you go. So you got basic filling done. Now we need to go and let's actually add the connection logic. So basically what we need to just say, this logic isn't really complicated. Basically what we just need to say is, okay, well, okay, so if it's a leaf, we just take the minimum connection of the node. And yeah, but I just need to be able to check. So here's the only issue I'm running into. It's just like making me not want to like this. Let's do this. So basically what we need to do now is just get the lowest min, or like the next connection point, right, for that node. And what's stopping me from just like instantly doing this is like what's gonna happen if we raise the water rate too high. So now it's like actually like the iterating of the simulation. which can get is like being weird. I feel like I'm overcomplicating this because I'm sitting here for so long. Why is this taking me so long to think about? Why? So basically, we just need to get the next connection, but the problem is how do we get that before how do we make sure that that connection is accounted for? Because if we raise by like 50 or something, like the easiest solution here, by the way, everyone that's like listening, if we just set the water rate to flat 1, then this is solved. But right now, I'm just worried about skipping over like connections. But maybe if I just search the connections, leaf node, water level. I don't want it to overshoot it though. Like I want it to be able to update right on time. Which I don't know how I could do that. Whatever. I think the solution, I'll just set this to clear. Yeah. But right now I'm trying to think about how can I do different water rates and not skip like connection points. So like a node wouldn't be able to fill up too fast. I'll probably just have to do some stupid check. I think about it, like there's actually no clean way to do it. Okay, so if the water rate's greater than 100, let's get the nodes connections. We'll do sim map dot so this is find connection, but I want connections. I want its connections, which I can just do sim map dot graph at leaf. Gives me its connections. And for now for each connection. Connections. Well, I mean, if you just keep... Oh, yeah, you're actually right. You're actually right now. I think about that. Fuck! I don't care. I'll do that later, bro. I'm not doing that. I'm not doing that right now. But you are actually right about that. But I don't want to do that. I don't care. I'll do it later. Right now, I just want to get it working. In the know. Oh, really? Yeah, I'll do that later, though, because I want to get this done. It's like the rough draft of it done now. And then, like, tomorrow, I'll fix it up and add cool shit. Alright, so every connection, basically... How do I make sure that it's not synced over? Well, well, you just get the minimum of it. All right. Ow, fucker. Should I do the checks before I increment, or should I? Okay, so basically what I'm gonna do is I'm gonna loop through all the connections. If anyone has saw that those sorts I just wrote, please ignore it. I'm just trying to get this fucking done. sort this, bro. Oh. I don't know if this code's gonna work, bro. I'm so like out of it right now. I do not give a fuck. Fuck, dude. Oh, because I never added the I don't understand what you're doing. That's 1. You get 1, then you add 2 because you have a barrier of entry of 0. Then you fill up 2. 2 is full. You get 1. And then it's crashing here, which is which I don't understand why it's crashing here. This is kind of fucking ridiculous, and it's getting me kind of mad. 4 connections and connections. Oh my god. My brain is mush. My brain is literal mush. Connection.toNode. Leaf is the parent. The minimum is equal to forward cost. Setting. How is it crashing? What? So you get 0, 1. Oh my god, that's why. Wait, no it's not. If connection.toNode not in sim nodes and is less than or equal to the min. Oh, well. No, that works because I don't understand what's going on, bro. You go to 1. Well, 1 goes to 2. Oh. And water level is greater than or equal to con.forward cost, bro. There you go. So the water level has to be greater than or equal to the forward cost. So basically what this is saying is we're going through the lowest. I just made it that way. There you go. So if I were to make this 80 and this 0, or if I were to make this 80, the first one fills up. Oh, well, this one should fill up to 80. Alright, well, okay, so I need to stop because I've been coding for a lot longer. You motherfuckers peer pressured me into coding longer. Basically, we got the structure down. This graph, maybe it could be simplified. It doesn't need to be. The fluid tree's done. Basically, this is all it needs to be. It's just next stream, which will be tomorrow, we just need to write the actual simulation logic. But my brain is kind of mush right now, and I've been kind of writing shit-ass code, and I don't want to keep destroying this code base anymore. I don't know why this is being so stupid, but yeah, tomorrow we'll finish it probably in like an hour. Like it's not that bad. It's just I kind of not accidentally, but I kind of went the extra hour when I probably shouldn't have because I'm not in the mood to do it right now. So, you know, when you're not in the mood to do something, you're probably not going to put your best effort into it. So that's what kind of happened here. But besides that, we have an actual working solution, a really good implementation for it, thanks to my friend. Working map, it's just literally just time to write the simulation logic, which shouldn't be that complicated. If I just come back in like tomorrow or something after a little break, I'll be able to like fucking write that shit in like probably like 10 minutes. Probably. Just have to think about it. Because it's not that complicated after you get to it. So it's literally like 3 cases, which technically I could do it right now, but I really don't want to. So I'm not going to. But thanks for tuning in, everyone that tuned in. And yeah, I'll see you tomorrow.